Good morning. Today we are doing Paul Hewitt's Conceptual Physics, Chapter 25 on vibrations and waves. So what is a vibration? A vibration is a wiggle in time and space. My hand is wiggling in time and space, and we could say it is vibrating. It's going back, it's a wiggle because it goes back to where it came from. It's repeating the same motion over and over again. It's wiggling in time and space. This is a vibration. Now, this, my pendulum, is wiggling in time and space. We could say it's vibrating, although in common speech we usually refer to things that are doing much faster. But this is, we could say it's vibrating. It's wiggling in time and space. Now, what would happen if I went in the dark and I attached a glowing, I made this glow, so that all you could see was this glowing, okay? So you'd see this little glowing ball moving back and forward. Now, what would happen if I walked as I carried this pendulum back and forth? And if you had a drone, if you were a footage from above, and you would see this little ball wiggling back and forth as I walked with it, what you would see was a glowing ball moving something like this. Well, especially if you had a camera where you're just capturing like the long exposure photography, you would see this is wiggling back and forth as I'm walking. This is you looking down from above as I'm walking with my pendulum, swinging back and forth in my hand. What you see here is a very simple wave. Now, we're going to talk a little bit about the anatomy of a wave. So we'll say, okay, so how far is it wiggling back and forth, back and forth? This we call the amplitude. Okay, so this is amplitude. And this we would call the wavelength. How long does it take to go do a complete wave back to its original position? This is a wavelength, and you could also cut it. This is a wavelength. You just need to get back to its original position from a full, this is half a wavelength. You'll see we are back to the original position, but it didn't go all the way and back. We want a full motion, a full vibration. That is a wavelength because it comes back to its original position and it went through its complete wiggle. So this is a wavelength. Get a different marker. From here to full rotation, this is a wavelength. This right here, that's a wavelength, okay? This here, that's amplitude. This helps us measure how big of a wave it is, okay? So this here, from here to here, so we're measuring the amplitude. Now, you can see, if I'm walking back and forth with my pendulum here, and like this, but what if I swing it harder? Okay, so it's swinging farther out. Well, in that case, when you're looking from above in that drone footage, you're going to see what's going to look more like this, because I'm swinging it farther out, right? So in this case, it would have a larger amplitude. But you can see, for this wave, it has the same wavelength. It is the same wavelength, larger amplitude. Now, say I have a pendulum that's swinging much faster. You're going to have, and you have a different, suppose I have a different, you see this one has a different wavelength. Instead of a wavelength of this big, this wavelength is like this. So this is twice, half the wavelength of the other guy. It's only, you know, it has, or we could say half the wavelength or twice the frequency. We'll talk more about that in a minute. But you can see we've got the amplitude, the wavelength, and often in waves they will call the bottom, when you look at one of these waves, they will call this the crest of the wave. They will call this the trough of the wave. Okay, so now we've talked a little bit about waves, the anatomy of a wave. Another way that you would see that, if I was swinging my pendulum and say it was dripping a constant stream of ink on the floor, and I'm walking, you're also going to see that curve, dripping on the floor. If you imagine it like I'm walking with my pendulum and it's dripping ink on the floor, and you will see this is my footsteps as I'm walking forward, and you'll see my pendulum that's swinging back and forth, dripping a trail of ink on the floor. And you can see the faster I walk, the more that trail is going to look more like, if I walk really fast, it'll look more like that, And if I'm walking really slowly and giving it a chance to really keep wiggling back and forth, it'll look more like that. but a wave is a really convenient way of charting that wiggle, that vibration in space and time. Okay, then we're going to talk about, period and frequency. So a period
Is it dot?
is how long did it take to do one complete wiggle. So let's say a period, and frequency is how many wiggles per second, okay? So say my pendulum wiggled twice every second. Its frequency, we'd say, is 2 vibrations per second, okay? For every 1 second, there's 2 vibrations, and we have a really convenient term for this, and that's just hertz. Hertz means vibrations per second.
Why is it spelled HZ?
It's a shortened form of hertz.
Okay.
So hertz means vibrations per second, and period is 1 over frequency. So if we said its period is half a second, that tells you a period is how long did it take to do one complete vibration. So if we tell you the period is, so let's say if it's 2 hertz, if we say its period is half a second, it tells you.
Is it megahertz?
Yes, we'll get to that. Megahertz means a million vibrations per second. Because instead of having to say, well, it's 500 million hertz, you just say it's 500 megahertz. Okay, so here, period is half a second. That's how long did it take to do its wiggle. Frequency, we say how many wiggles per second. So frequency and period, period is really just 1 over the frequency. Frequency is 1 over the period. Basically, frequency is a way to say...
Wait, period and frequency are the same?
They are, but they're different ways to say it. Frequency is saying how many wiggles per second. Oh, it's 200 hertz, 200 wiggles per second. Period is saying, its period is 1/200th of a second. If its period is 1/200th of a second, that tells you there's 200 wiggles in a second. That's 200 hertz is the same as saying something's period is 1/200th of a second. Okay, now we're going to talk about bugs. So you've heard like a bumblebee will sound like bzzz, and a honeybee will be more like bzzz, not really bzzz, and if you hear ee in your ears, you start slapping your ears and moving away because you know there's a mosquito trying to drink your blood. So why? Why do mosquitoes give this ee and the bumblebee gives more like a bzzz sound? And the reason is that it's their wings. Their little wings are flapping. And the bumblebee is flapping at something around, a bumblebee is around 100 hertz, I believe. Its wings flap something like 100 times a second. So those big bumblebees, a bumblebee has its wings flap at something like 100 hertz. So 100 flaps a second. A honeybee, that is smaller, is flapping at somewhere around 200 hertz. 200. That's why a honeybee's buzz sounds higher pitched, because we hear those faster frequencies sound higher to us. And the reason the mosquito sounds like ee in your ears is that a mosquito's wings flap something like 600 hertz, 600 times a second. And that's why you hear that tinny whine of a mosquito, is that that's its wings flapping. Every little flap that those wings make, those little vibrations that the bug wings are making, is compressing the air and sending out those little air compressions that we hear as sound. Those vibrations that we hear, the waves that we hear as sound. Okay, so I wanted to say a little bit more about that. So when we see a picture of a wave, we often see it looking like this. We like to remember what we were liking to depict as a wave. And this is often called a transverse wave because you're drawing it in basically 2 dimensions. We're showing it in 2 dimensions. We're showing that wave. Now, scientists love using slinkies for longitudinal waves because a longitudinal wave is a wave that's really happening by compressions. This is like with sound. What we hear is sound. What's going on with sound when you've got that little bug flapping its wings back and forth, it's compressing the air. Every time it wiggles its little wings, it's compressing the air molecules. So it's like kind of a compressed and then a little space with not as many air molecules, and the air molecules get shoved forward and kind of jam into it like a little traffic jam, and you end up with these what we call longitudinal waves. And you'll see what it is it's where all the air molecules got shoved together, and then there's sort of like a space with fewer molecules, and then more where the molecules are shoved together, and then fewer molecules, and then shoved together, and it sort of makes this pattern of colliding air molecules, and that is what we hear as sound. And so when they try to depict what a longitudinal wave looks like, if you play with a slinky, I don't have a slinky, or I would try to, so you know those metal look like this. If you have a slinky out, like stretched out horizontally, and you sort of push it, you will see it stretch, and then it'll have like a wave, and the wave will propagate down. And this is making me wish I had a slinky to show you. They always got so tangled, I end up throwing them out. But if you play with a slinky along, pull that slinky, and you push, you will see those like longitudinal waves, what they call them. And this is much more like a slinky. The waves you send down with a slinky is much more like if you could see on a microscopic level what sound waves look like. Sound waves look like these compressions of air, kind of like those compressions of a slinky propagating down the slinky. Okay, now we're going to have some fun with, wave speed. So now we're going to talk about wave speed. So wave speed, velocity, so V is for velocity, for speed with the direction, but we're doing this for the velocity of a wave speed is equal to its wavelength times its frequency. Okay? Because if we say a frequency, remember, is in how many wiggles per second, how many waves per second, okay? So if we say, okay, a frequency will tell you, say we've got a frequency of 2 hertz, okay? 2 hertz. So our frequency here in this situation is going to be 2 hertz. Well, what is a hertz? A hertz is 2 wiggles per second. So we've got, so frequency here we're going to change to 2 waves, 2 wiggles per second, okay? And what's this? Well, let's say, that wave is about, let's say it's 2 meters long. The wave is 2 meters long. So the wavelength gives us 2 meters. Well, waves, we kind of know this is the waves. So we've got, how fast is that wave going? That wave is moving at 4 meters per second. Okay, because the wave speed is how long is that wave and how fast is it going? And you can get that from the wavelength times the frequency. Gives you the wave speed. Okay, because you remember, speed is just distance over time, right? Distance over time, and you get that with this and this. Okay, so for example, you can go down to the beach if you live near an ocean, unlike us landlocked desert dwellers. If you go to an ocean and you want to figure out how fast are those waves moving, then you will look and you will say, okay, I see with your little drone or with you from the balcony, you look down and you say, from one ocean wave to another ocean wave, say I see, I don't know, let's say 10 meters. 10 meters apart, and you said, and what is the time? What's the frequency? And you say, well, you look at this little buoy, little flotation device, and you see it going up, riding the crest of a wave, and then dropping down the trough of a wave. And you can find the frequency by timing that buoy, and then measuring with your photograph or whatever, your drone, what the distance is. Buoy. Anyways, and you can measure
buoyant or something.
Right, and you can measure how fast are those waves going. You say, okay, it's about 10 meters apart. Waves are 10 meters apart, and the little kids riding the waves are going up and down a complete vibration, say every 10 seconds. Then you know it's going 20 meters in 10 seconds. So 20 meters in 10 seconds will be 2 meters a second, and you can say that wave is moving at a speed of 2 meters a second. Now we actually sort of back solve to find out how long sound waves are, because we know the speed of sound. So in air on Earth, now remember, sound travels at a different speed in different mediums. So it will travel 15 times faster in iron than it does, or in steel than it does in air.
Is that with telephone poles and stuff?
It will travel something like 4 times as fast in water than it will in air, in our air, in sound. Because
is that with like the Morse code, like?
Yeah, it goes much faster through the lines. That's the reason for the old story of like the American Indians, or if you watch Lord of the Rings, when they're trying to find which way the Urukai have kidnapped their friends, marching around, they put their ear to the ground to try to hear the sound. Same way, like the American Indians would put their ear to the ground to try to figure out, which direction galloping horses were and all that. Is that sound travels much faster through more solid things like water and the earth solids, especially elastic things. So, for example, water and steel, sound will travel 15 times faster in steel because it's more elastic. Like the more elastic something is, the faster it can transmit sound. Where water is less elastic and it only travels 4 times as fast as air. Where steel is 15 times as fast as air. But anyways, so back to I feel like I got so distracted. Did we talk about violin strings in this take yet?
I don't know.
Okay. Oh, can you pause for 1 second? I need to get in my words. So, one thing to notice here, again, with sound traveling or with our sound, is that waves are moving energy, not matter. Now, we're not saying the thing isn't wiggling at all. The matter is wiggling. But for example, when I am speaking and she can hear me over there, it's not because the same air molecules that are coming out of my mouth have gotten into her ear. The air molecules coming out of my mouth, like the air compression, it's the compression. It's the propagating pattern of compressions that has reached her ear. If you tag the actual molecules themselves, it's more like they're vibrating in place. And they bump the next one, they bump the next one, they bump the next one. Or for another example, when you see the ocean waves hitting the beach, it's not that all that water is moving and is going to completely swamp the earth. You'll see the wave will lap and then come back, lap. The waves are, the energy is moving this way, but the matter itself
Wait, so that
is
one
only rising
pushes
and
the
falling.
other water, which pushes
Right.
the other water?
Right, so if you can kind of imagine, you see like a little buoy going up and down, or a little thing, pulling back and forth. The matter itself is just sort of shaking in place or vibrating, but the wave is traveling. And way to explain this, Jenny, what happened to the necklace I had?
The necklace?
Green one, yeah.
Oh, there it is.
Mommy,
Thank you.
the computer ran out of battery.
Okay, go plug it in, sweetheart.
I don't know how to.
She knows how to.
Jen,
Also
go
plug it in.
plug it in.
Wait, so here we're going to demonstrate.
Want me to connect them?
No, it's okay. Okay, so hold this end, Jenny, hold this end.
Can I hold it?
Okay, good job, Sarah Grace. Okay, so here we've got this string of beads, and okay, don't wiggle it too crazy. You want to get a nice. Okay, wait. Let's hold it still.
You just let me try.
No. Wait, I'll switch this up.
Wait, Mom, I'm
Right,
gonna
just
pause
hold
it.
still. Hold it. What?
I'm gonna pause it.
Don't pause it.
Wait, can I please?
No, don't pause it. Hold it up high, Jenny, so they can see it. Ready? So if you look, I'm sending waves down. Okay, they're going a little crazy. I'm sending waves down this. The beads themselves are moving a little bit, but I'm not sending the bead down from my finger to her. I'm just sending the wave down. And these waves are going nuts. I'm sending the waves down, but I'm not actually sending this bead all the way to her. So in that way, we say that waves move energy, but they don't move matter. Wait, hold on. Can you pause the video? Just pause. Don't stop it. Just pause it. Okay, so we've covered how we can back solve and find out the wave speed. With like that ocean example, you see the buoy floating and you see that moving forward, and you can figure out how fast those waves are going by multiplying the wavelength by the frequency. We've talked about longitudinal waves. Longitudinal waves are usually in one dimension, so we see like that pattern of air compressions, versus transverse waves, which we will draw like in 2 dimensions, so you can see it like that. So now we're going to talk a little bit about interference. Oh, sorry, we forgot. So I want to use this. We did this to find out wave speed, but what happens if we know wave speed, like sound? We know that in air, depending how hot and humid it is, the speed of sound in air is between, where's my erasers? Oh. Is between 330 meters per second and 350 meters per second. So the speed of sound,
Does humidity make it slower?
No, it actually makes it faster. Heat and humidity in air vary between 330 meters per second in dry air to 350 meters per second pretty much for every problem in our book, we're just going to go with a nice little average 340 meters per second. So because it's in this range, we're just going to make the speed of sound, for the convenience of our calculations, in air, 340 meters per second. Okay, so now we will say, so how long is the wavelength of that little mosquito? Remember we said it's 600 hertz? So because we know this, we know the speed of sound in air will be 340 meters per second, and we know the frequency we can solve for what is the wavelength of a mosquito flapping sound. That ee that we hear, remember? So we said we knew that the mosquito's frequency was 600 hertz, right? And we know the speed here is 340. So let's first solve symbolically first. So we have the velocity equals lambda to the wavelength times the frequency. We want to know the wavelength. So remember we move everything that we know. We know this and we know this. We move everything we know. So I'm going to divide both sides of the equation by frequency, because you can do that. This over this becomes 1, so that's gone. So now we can say, okay, so the velocity of the wave divided by the frequency of the wave will give us the wavelength. So for a mosquito, we say, okay, the velocity is going to be 340 meters per second, and the frequency is 600 vibrations per second, so hertz. Remember, if we want to cancel stuff out, this is going to be vibrations per second. So I'm going to write vibrations per second. And you'll see second is here, second is here. It's actually in the same position, so it will cancel out. And we'll get the answer in meters. And our answer is going to be 340 divided by 600 meters. So meter up there on the top. Because this is going to cancel, and this is going to cancel, and this is vibration. It just kind of disappears. So we've got meters. So you've got 340 divided by 600, and that's going to come out to something around like, I'm not going to do the math, so I'm going to do something like that. So that's kind of cool when you realize that even though you're hearing it like this really high-pitched sound, that if you could see that sound wave in space and time, it'd be like this long, the mosquitoes. Now remember that bumblebee at 100 hertz? The bumblebee, so everything else is the same. We could plug it in for the bumblebee, except this is going to be 100. That bumblebee, that you're boo, that sound wave, how long is that sound wave? That sound wave is about 3.4 meters. That's like 9 feet, 10 feet. So that buzz you hear of a bumblebee is like 10-foot sound wave, which is kind of cool. And another thing you can do is, like if you ever played in an orchestra, or something like that tuning A, I think it's 440 hertz. So you can plug that in and see how many feet is the sound wave that you're hearing there. So yeah, I think that's making too much sound. Nice. So here I want to, speaking of instruments, I want to talk a little bit about so remember how we talk about how the wings flapping is making those air compressions. So here, you see the top string on the guitar here makes that sound, and you can actually see it. You can see it vibrating. I don't know how good the camera will pick this up, but look at that string. Like, do you see that? Do you see that? You can see those strings vibrating. I don't know how good the camera is at picking it up, but you can see those strings vibrating. And if you look, the minute I stop it from vibrating, so you can see that string vibrating. Do you hear? Okay. See? And when I stop it from vibrating, the sound stops. Because that vibrating string is making those air compressions that you hear. See? And so when you stop it, there's no more sound coming out of that. Another thing I want you to notice is that the higher sounds, just like, remember the mosquito with its higher, the flapping of its wings making that higher sound? This tighter string is actually vibrating much more like the mosquito's wings. This string, the looser and thicker those strings are, the more they're making, looser, longer, and thicker the string is, the more they're like the bumblebee. The tighter they are, the more they're like the mosquito. And even shorter, because you'll look at this string, making that deep, low note, and then I'm going to stick my finger and make it shorter. And you hear it's higher. Because it's more like making those air compressions more like the mosquito than the bumblebee. We see the same thing with an instrument like this. So in here, instead of having that vibrating string sending those air compressions that we hear as sound, here there's actually a vibrating tube of air, but there's holes poked into it. So if I blow, it's somewhat high because functionally that column of air ends about here. This is where it can start to leak out. So what happens if I cover up the holes? I'm now making this vibrating column of air much longer. You see how as I lift my fingers off, I'm shortening that tube of air and the sound goes up. So listen. As I make that column longer, those vibrations are more like the bumblebee's wings and less like the mosquito's wings. As I make the column shorter, we get much faster vibrations like the mosquito. You see this with pretty much any instrument. If you look at like the big version, like the bass or bass, the really big one they have to stand up to play, and you compare it to the violin, and you see the littler ones are like the mosquito. They're making much tighter, shorter vibrations. And you'll see the big one with the big stretched out. You can see this with flutes too. You know, the flute where most of us are used to, the modern orchestral flute, that's the soprano flute. There's alto flutes, there's, bass flute, bass flutes. You can see they get bigger and bigger. And generally, the bigger the instrument, the bigger that column of air, or the bigger that longer that string, the longer and looser that string, the more you can get low notes because you're getting those really longer sound waves. Or I guess longitudinal, but you're getting the long waves where you're getting the short waves, you get the higher sound. Okay, and remember all of the sounds are traveling at the same speed, around 340 meters per second. When someone plays in the orchestra, you don't hear the cellos before you hear the violin. You hear all of it together. They're all traveling, those sound waves are traveling at the same speed, but what you are hearing, the different instruments, what you are hearing is the different wavelength. The longer waves versus the shorter waves, like you're hearing, that's the sound that you're hearing different, or frequencies and all that. Okay, so now we're going to get to, we talked about the difference between longitudinal waves, remember in one dimension, and transverse waves, where we draw it in 2 dimensions. Remember the transverse waves, the longitudinal waves, you can think of it as in a single dimension, so we usually show it by compression, so this, and if we're going to show it transverse, we would draw it like, okay, so that's the crest, this is the trough, this is the other crest, and you can see how that correlates. It's easier to draw this way, so people mostly like drawing their waves, transverse waves versus longitudinal waves. If we had a slinky, you could, see it would look like this. Anyway. Okay, so now we're going to talk about standing waves. Standing waves are pretty cool. Jenny, can you demonstrate? Yeah. So anyone who's played any sort of jump rope, we might have to just do this with one. It might be a little too long. It would be great if we had more space and you could see. So standing waves is anyone who's played jump rope. Hold it up high so the camera can see it. So just hold it as still as you can. I'm going to do the waves, okay? So you can see I'm going to ascend.
Yeah.
As you can see.
That's fun to do.
That's fun. And do you see how that middle part is just hanging out, like barely moving? That's a node. This is a node where it's barely moving, and then the other ones, it's a standing wave, we could say, because here it's as if the crest of the waves, whoa, oh, okay, now we've got one giant half a standing wave, you can see? Now if I do it just right, we can get a node in the middle there and have a full standing wave. Let me see, you gotta get it. Anyone who's done like competitive jump roping and all can probably do it way better than this. Anyway, as you can see, you get standing waves, and what's actually going on with a standing wave is you're getting resonance, reinforcement, and cancellation. So when you send a wave, it often bounces back. I mean, tie a rope to the end of something, like a chair or whatever in the other room, send a wave down, and you'll see it go and then kind of bounce back. So what a standing, well, first we'll talk about cancellation. So when you've got, say I've got this wave doing this, okay? Okay, so what happens if I stack it with another wave also doing this, okay? Well, you see the volume under this, these reinforce each other. So now it's going to go twice as high here. They're both doing nothing here. Now it's going twice as deep here. You see how as I stack the waves, If it's resonating, this is constructive interference. The crests are higher, the trells are deeper. Now what happens though, if that wave that's bouncing back, that's also, so we've got two kids holding ends of a jump rope and they're sending waves at each other, okay? So they send it in rhythm with each other and it gets bigger, the waves get bigger and bigger. Now what happens if it's destructive interference? What happens when the wave, the opposite wave coming to cross it is doing this? It cancels. It cancels and you don't see anything, right? Because this crest and this trough cancel each other out. You make it like negative and positive numbers and you get nothing. And it just looks like this. You just get like this. So what's happening with standing waves when we're sending that jump, when you're doing double dutch or whatever, when people are doing that jump rope, what's happening is they're actually sending multiple waves and the waves are passing over each other and canceling each other out and then reinforcing each other. And that's why you see it looks like a wave is just standing there, but it's actually multiple waves crossing each other, canceling and reinforcing each other by the interference patterns. So there's a beautiful little illustration in your book right here on page 379, and you'll see here if they're the same, they'll reinforce each other and get bigger, and if they're the opposite, they will cancel each other out.
What if you got one that's canceling and one that's reinforcing?
I mean, that's kind of what's going on with standing waves, because you've actually got waves going in the up and down direction and the side to side direction. That's why it looks like a standing wave. What's actually going on is you've got actually multiple waves canceling and reinforcing each other at different times. And that's why it looks like they're the nodes. This is one of my favorite things to do. When my sister first did it, I thought we discovered magic. I think I was like 11. So you get it and you start to, ouch. You start to spin it and it looks like an invisible hand is holding, sorry, if I can ever get this. You see how it looks like an invisible hand is holding it, the other end of it?
We used to do that above people's faces. So
yeah, this is a node. Okay, that's a node, that invisible hand. And we raced to my dad, told him we had discovered something new, brought it to him, and we got a little lecture on standing waves, and I was pretty deflated.
So
I thought I had just discovered magic.
Be at the office.
No, you don't have to be, but shh, be quiet, because Mom's recording a lecture. They have a really beautiful illustration for you in the book here, where you'll see the node is the null point, and as the waves are traveling back and forth, and they'll show it to you with the standing waves. And you get these cool ripple interference patterns with these circular waves. You can even just go and see this, like if you have a pool or somewhere with access to still water, and you start like throwing pebbles in, and you can see those really cool interference patterns. Okay.
Or just go to your bathtub.
You could do it in your bathtub if it's a little harder, you don't have as much space, but yes. Okay, now let's talk about the Doppler effect. The Doppler effect is used by policemen to find out when you're speeding, and it is used by astronomers to figure out which galaxies are hurtling away from us. It's very cool. And the Doppler effect is basically this. So, say you've got a bug, I don't know, going, popping its head in and out of the water, and it's making ripples.
Wait, what's the bug doing in the water?
I don't know, like one of those little water walking bugs. Okay. You see, popping up and down, it's making little ripples, okay? And you see these ripples and they're traveling outwards. Okay, these are waves traveling outwards. Now what happens, or you could even say it's like a little girl dropping, I don't know, putting her finger in and out of the water, but then, standing there and sending out these ripples. Well, what happens when she starts to move? Well, she's doing it tap, tap, tap. So the first tap, that wave, and while that wave is traveling out, so she moves to here. So what you end up seeing here is that it's going to look, the new waves, if you look, because she's moving away, they're going out, but as she's moving this way. So what happens is that if this girl is moving, if you're standing here and measuring the waves, if you're over here, the guy over here is going to get waves that are further apart than they actually are in reality because she's moving away from him. Where the guy here is going to get waves that are actually coming faster than they were made because she's walking toward him. Now light, the longer the wavelength, the redder it is. The shorter the wavelength, the bluer it is. So when they talk about, in sound, the shorter the wavelength, the higher the sound is. And in sound, the longer the wavelength, the lower it is. So when you hear ambulance driving and it's coming behind you, you often hear, and then when it's traveling away from you. It's not that they've suddenly decided to change the sound that they're playing as they pass you, the center of the universe. it's that it sounds different to you because when the ambulance is coming towards you, you're hearing those sound waves basically being pushed because it's moving closer and closer and closer together. And as it's traveling away from you, you're getting those sound waves further and further apart. And that's why an ambulance sounds different as it is approaching you and as it leaves you behind. In the same way, when we see another galaxy that's moving toward us, it will be red. It will be blue shifted.
Toward us?
Yes, if there's a galaxy or something moving.
Will it crash?
If there's something moving toward us, it is what we call blue shifted. Because the same way that the sound waves let me finish. No, let me finish. As the same way that sound waves when they get stacked closer and closer, they get higher pitch. Light as those light waves get pushed closer and closer together, or get as they get their wavelength shortened, we see it bluer, and as the wavelength is stretched out, we see it redder. So that's why we talk about when galaxies are red shifted, that means they're moving away from us. So they said we're the spinning, really cool example of a star. So we've got a burning hot star like our sun, spinning, but it's a spinning star. And when we're looking at it, we can even tell that the light coming from one side of it, the light coming from this side is bluer, and the light coming from this side of it is redder. That tells us that this side of the star is spinning toward us, and this side of the star is spinning away from us. So we can even figure out which way this star is rotating, because the light we're looking at this edge is blue, and that light looks red. That tells us that star is spinning this way. The same way that, the waves here, these waves of light that are coming toward us are getting blue shifted, and this side that's getting shifted away from us is red shifted. This was how they figured out that the universe is expanding, which is pretty darn cool, was because they found out all the galaxies around us are red shifted. Why are they red shifted? Do we just happen to be at the very center of the universe with everything moving away from us? Or it's because the entire universe is expanding. Everything is moving away from everything else, and that's why things are red shifted. And there's so much cool astronomy that can be done. This is called the Doppler effect. When you hear the siren, I'm not doing a very good job, but you've all heard ambulances come up behind you when you're driving. That is the Doppler effect, and it's the effect of the sound waves get compressed when they're moving towards you, and then stretched out as they're moving away from you. And remember, when light is moving towards you, it looks compressed towards you, it shifts bluer, and as those wavelengths of light get away from you, it shifts redder. Okay, let's see what we talked about. Sonic booms. If you've ever heard of sonic boom, what's going on is that's from supersonic aircraft. So remember the speed of sound in air is 340 meters per second. In air is 340 meters per second. So if your aircraft is going less than 340 meters per second, even if it's moving toward you, it'll look more like this. Like that ambulance is going less than 340 meters per second. If your ambulance truck is going more than 340 meters per second, supersonic speeds, faster than the speed of sound, you would hear a boom. That would be a sonic boom. A sonic boom is when the thing producing the waves is actually going faster than the waves themselves. This is if you're going faster than the speed, and so it would look something like this. All right, and as you stand here and the sound travels over you, as you get in basically the wake of this, you hear that boom. So for an example, what is similar to, so try to think of it as, if you've ever been sitting next to a motorboat and the water's shooting out from either side, like if you've ever seen a little motorboat, so this is an aerial view, we're looking down like a drone from a motorboat, and there's the water is spurting like this on either side, as similar to this cone that it makes in sound. Now, one thing that's cool is a whip, like those really long whips, and they crack the whip. The tip of that whip is actually going more than 340 meters a second. That's why you hear a crack from a whip. The crack from the whip is this little mini sonic boom, because the tip of that whip is going faster than the speed of sound in air. And so that's why you hear it as a boom. That is why if you had supersonic aircraft, it will make a sonic boom. Like it's going to. If something is going faster than the speed,
do that?
Well, if you're a spaceship in space, what is the speed of sound in space?
No clue.
0 meters per second. There's no medium. Sound has to travel through a medium. That's why they always say, oh, space battles would actually be really silent. You know, movies, there's always a huge noise as it explodes. That's true and also not true. If you were hanging out in a vacuum, separated by vacuum from the space battle, it's true to be utterly silent. However, if you were actually if you were in the explosion, you would hear the sound traveling through that air as the thing blew up. If you were in the air pocket created by that explosion. So if you were in the vacuum of space watching two spaceships collide, it would be utterly silent until you got engulfed by the air that is escaping from that ship with the sound coming out of it. I mean, if you're in the explosion, I mean, I suppose you could always make up a story where you're in a spacesuit and there's silence and there's noise and I don't know. But then you would have to have some, anyway, okay. Let's see. So we covered that, speedboats, sonic booms, supersonic aircraft. I think we're good to go. Jenny, you cut that.
The end.